It began not with a whimper, but with a shudder, a synchronized shudder that rippled across 93 million miles of space and pierced the very crust beneath our feet. The clock, a universal arbiter of order in a chaotic cosmos, read 1347, universal time on a Tuesday that should have been utterly forgettable. But in that precise, razor-thin slice of eternity, something impossible happened, something that defied the comfortable, compartmentalized understanding we have of our place in the universe. On the left side of the cosmic ledger, the sun, our life-giver, our constant celestial companion, exploded. A monstrous ball of magnetized plasma erupted from its surface, a beacon of violence visible across the solar system. On the right side of the ledger, at that exact same millisecond, the planet Earth answered. Not with a whisper, but with a roar. The ground in Alaska, along one of the most volatile tectonic seams on the planet, tore itself apart in a magnitude 7.0 earthquake. The energy release was equivalent to detonating over 30 of the most powerful thermonuclear weapons ever built by humankind, all focused into a single brutal release of pent-up geological fury. Solar explosion, terrestrial rupture, same instant, same timestamp down to the second. This is not a metaphor, it is a data point, a cold, hard, and terrifyingly precise alignment of events, separated by the unimaginable void of interplanetary space. Coincidence is a concept we use to explain the unexplainable, to soothe our minds when patterns emerge from the noise. But coincidence has limits. It stretches only so thin before it snaps, revealing not randomness, but the shadow of a connection we have failed, or perhaps refused, to see. While the world's gaze has been fixated on the heavens, tracking the enigmatic path of an interstellar visitor dubbed 3 Atlas, a far more intimate and unsettling pattern has been stitching itself together right under our noses, in the data streams of solar observatories and seismic networks. In quiet corners of research institutions, in hushed conversations at conferences that straddle the line between geophysics and heliophysics, a disquieting question is being murmured. Scientists, the very people we trust to have the answers, are feeling the first icy fingers of a new kind of terror. It is not the fear of something alien arriving from the depths of interstellar space. It is the fear of something familiar turning against us. It is the dawning suspicion that our own star, the gentle yellow dwarf that nurtures all life on this blue marble, might hold a key to the most violent and unpredictable processes within the planet itself. This investigation will take you to the heart of that suspicion. We will dissect the data, interrogate the assumptions, and follow the evidence wherever it leads, even if it leads to a paradigm shift that rewrites the textbooks. By the end of this journey, you will understand why the next solar storm might be far more than a light show in the sky or a temporary blip in satellite communications. It might be a geological trigger, and our failure to recognize that could have consequences we are utterly unprepared for. The data is screaming that we've been watching the wrong sky, obsessing over distant threats while a potentially profound connection hums with power right in our own celestial backyard. Before we descend into the depths of this mystery, I want to pause and acknowledge you, right where you are, participating in this global moment of inquiry. Where in the world are you watching from right now? What is your local time as you read these words? The very nature of this phenomenon is global, and your perspective, your location on this spinning rock, is part of the story. Drop a comment below. Let's map our collective curiosity. And if this exploration into the hidden threads that bind star to planet resonates with you, if you feel that pull to understand the deeper mechanics of our cosmic home, then consider subscribing. What we are uncovering here is not a single news cycle story. It is an ongoing investigation, a slow unraveling of a mystery that will require patience, scrutiny, and a community of the thoughtfully engaged to piece together. Your eyes and your mind are part of this process. Now, let us return to that control room, a hypothetical but representative nerve center where the fateful data converged. Picture it. A wall of monitors, the cool glow of electronic displays, illuminating the focused faces of analysts. On the leftmost screen, data streams in from the Solar Dynamics Observatory, from NOAA's GOES satellites, from the venerable SOHO spacecraft silently holding its vigil at the Lagrange point between Earth and Sun. The imagery is both beautiful and horrifying. Sunspot region 4299, a sprawling dark cancer on the Sun's photosphere, is not just active, it is structurally malignant. Its magnetic topology, visible to specialized instruments, is a cat's cradle of twisted, stressed field lines wound tighter and tighter like a spring coiling past its breaking point. At 1347 Vaughan UT, the spring snaps. The screen flares with intense white light, a signature of an M8.1 class solar flare. This is not the absolute top of the scale. That reserve is for X-class monsters. But an M8.1 brushes the lower boundary of that extreme territory. It is a beast by any measure. In a matter of minutes, the eruption unleashes a tsunami of energy across the electromagnetic spectrum. A flash of X-rays and extreme ultraviolet radiation that races outward at light speed, followed by a hail of high-energy protons and electrons accelerated to relativistic velocities. But the main event, the kinetic payload, is yet to come. Coronagraph footage, where an occulting disk blocks the sun's blinding face to reveal its wispy, ethereal outer atmosphere, tells the next chapter. A shockwave, a ripple of compressed solar wind, blooms outward from the epicenter. And behind it, like a titan emerging from the depths, comes the coronal mass ejection, CME. This is not mere radiation. This is a physical piece of the sun being hurled into space. A billion-ton cloud of magnetized plasma, a bubble of stellar stuff carrying with it the twisted magnetic fingerprints of its origin. Crucially, the coronagraph shows a full halo event. The CME expands in an almost perfect ring around the occulting disk. From our vantage point, that geometry has one terrifying implication. The cloud is headed directly for Earth. It is a cosmic bullseye. Traveling at several million kilometers per hour, this magnetized freight train has just left the station, and our planet is on the tracks. Now, swing your gaze to the right-hand monitor. This feed is terrestrial, grounded, literally of the Earth. It displays the real-time data stream from the United States Geological Survey's seismic network, a spiderweb of ultra-sensitive instruments buried in vaults, drilled into bedrock, and scattered across the globe, listening to the planet's heartbeat. The screen is a forest of squiggly lines, each representing a seismometer. At precisely 1347 UT, the same second the sun's magnetic field snapped, a spike, violent and unambiguous, erupts across dozens of traces in southern Alaska. It is not a local glitch. It is a coherent wavefront. Primary waves, P waves, the fast-moving compression pulses, arrive first, followed seconds later by the more destructive secondary shear waves, S waves, and then the long, rolling surface waves that do the most damage. The automatic processing systems triangulate the source, calculate the magnitude, 7.0. The epicenter is located in a complex knot of faults, a place where the Pacific plate grinds inexorably beneath the North American plate along the Aleutian subduction zone. The ground has moved horizontally and vertically with violent force. Within minutes, the aftershock sequence begins, a frenetic staccato of smaller ruptures. Over 150 would be recorded in the next few hours, several of them powerful earthquakes in their own right, exceeding magnitude 5.0. 2 events, one stellar, one terrestrial, separated by the vacuum of space, governed by textbooks from entirely different scientific disciplines. yet they share a timestamp with a precision that feels intentional, a precision that bypasses the messy, probabilistic nature of both solar activity and seismicity. This is the core of the anomaly. We are not talking about an earthquake happening sometime around a solar storm. We are not dealing with a window of days or even hours where chance could comfortably explain the overlap. We are presented with a synchronization down to the second. It is a data point that demands an explanation beyond bad luck. This single event, however stark, is not isolated in the historical record. For decades, a handful of researchers, often working at the fringes of their respective fields, have pointed to curious temporal proximities between major solar outbursts and significant earthquakes. The 1989 Loma Prieta earthquake occurred during a period of heightened solar activity. The 2011 Tohoku earthquake in Japan was preceded by a powerful solar flare. The list of anecdotal alignments is longer than mainstream science cares to admit. But these past events always had wiggle room. The timing was off by hours. The solar event wasn't uniquely powerful. The earthquake could easily be explained by local tectonic loading. The Alaska event, with its split-second timing and clear, powerful signatures from both realms, strips away that wiggle room. It is the cleanest, most dramatic, and most provocatively precise example ever recorded. It forces the question from the realm of fringe speculation into the domain of legitimate, urgent scientific inquiry. Why does this matter? On a fundamental level, it matters because our entire understanding of natural hazards is built on the principle of separation. We have created silos of knowledge for our own convenience. Solar physicists model the sun's interior, its magnetic dynamo, the mechanics of flares and CMEs. Their concerns are the magnetosphere, the ionosphere, satellite drag, radio blackouts, and beautiful, harmless auroras. Seismologists model stress accumulation along fault lines, the frictional properties of rocks, the propagation of seismic waves. Their concerns are ground shaking, liquefaction, tsunamis, and building codes. These two communities publish in different journals, attend different conferences, and apply for funding from different agencies. The sun, in the seismic hazard model, is a distant light bulb. The Earth's crust, in the space weather forecast, is irrelevant bedrock. They are separate domains, and our safety has been predicated on that separation being real. But what if it's an illusion? What if there is a hidden conduit, a back channel, through which energy and information can flow from the roiling magnetic atmosphere of the sun, through the protective bubble of our magnetosphere, down through hundreds of kilometers of rock, to the critically stressed faults that lie in wait? The implications are staggering. It means our risk assessments are incomplete, potentially fatally so. It means a region considered seismically quiet, based on tectonic history alone, might be vulnerable if a perfect solar storm arrives. It means our critical infrastructure, power grids, pipelines, communication cables, could be hit with a 1-2 punch of geomagnetically induced currents and direct seismic damage simultaneously, a cascade of failures for which we have no contingency plan. It redefines planetary defense, shifting the focus from inbound asteroids to our own, seemingly benevolent star. So we arrive at the uncomfortable, essential question. Could our star be triggering earthquakes, not in some vague astrological sense of cosmic influence, but through a concrete, physical, if currently elusive, mechanism? Could the vast electromagnetic energy of a solar storm, when it slams into Earth's magnetic field, induce effects that propagate into the crust and provide the final minuscule nudge to a fault already on the razor's edge of failure? This is not a question about the sun creating the energy of an earthquake. That titanic force comes from plate tectonics, accumulated over centuries. This is a question about the sun acting as a trigger, a cosmic finger on the geological hair trigger. The distinction is critical. It moves the problem from an insurmountable energy budget crisis solar storms carry nowhere near the energy of a major quake, to a delicate problem of nonlinear systems and critical thresholds. It's the difference between trying to topple a skyscraper with a firecracker, impossible, and using that same firecracker to trigger a detonator attached to the building's foundational supports, plausible if the supports are already primed to collapse. This investigation is a forensic audit of that possibility. We will proceed as careful detectives, not passionate advocates. Our evidence is the publicly available data. The solar flare reports from NOAA's Space Weather Prediction Center, the seismograms from the USGS and global networks, the magnetometer readings from research institutes and dedicated amateurs. We will follow a chain of logic. First, we will establish the facts of the solar event in granular detail. What made this flare and CME unusual? Was it just another storm, or did it possess unique characteristics, like its observed double explosion structure? That might make it a more potent terrestrial influencer. Second, we will zoom in on the Alaska earthquake. We'll examine its specific fault mechanism, its aftershock pattern, and the tectonic context. Was this fault known to be critically stressed? Were there peculiarities in the seismic sequence leading up to it? Third, and perhaps most controversially, we will search for the smoking gun that would link the two, the electromagnetic fingerprint. We will delve into reports of anomalous Schumann resonance spikes, strange magnetometer readings from places like Tomsk, Russia, that allegedly occurred at the same time. This is the most contested data, where signal and noise blur, and where extraordinary claims must be met with extraordinary skepticism. Our journey will then widen. We will explore the proposed physical mechanisms for such a connection. How could energy transfer work? We'll discuss telluric currents, the electrical currents induced in the Earth's crust by a changing magnetic field, and the piezoelectric effect, where crystals like quartz generate electric charge under mechanical stress, and vice versa. We will assess the statistical evidence. Do decades of data show a correlation between solar activity and seismicity? Or is this all a grand exercise in pattern finding and confirmation bias? We will examine the anomalies that make this case particularly sticky. The precursor seismic silence, the speculative geometric alignments with ancient sites that, while likely fantastical, speak to the human desire to find meaning in such events. Finally, we will place this earthly mystery in its proper cosmic context. We will look at exoplanets like WASP 107b, whose atmosphere is being violently stripped away by its star, proving that star-planet coupling can be devastatingly direct. We will consider the discovery of vast filaments of galaxies rotating in coherent unison across hundreds of millions of light years, a reminder that the universe loves synchronization on scales we can barely comprehend. And we will reflect on the lesson from gravitational wave astronomy, that with the right instruments and persistent investigation, phenomena once deemed speculative or undetectable can become established science almost overnight. This is not a call to panic. It is a call to pay attention. It is an argument for intellectual courage, the courage to ask difficult questions that straddle disciplinary boundaries, and the courage to invest in the meticulous, often unglamorous work of gathering the data needed to answer them. The sun erupted, the earth quaked. At the same moment, we can shrug and call it coincidence, preserving our comfortable models. Or we can lean in, investigate with rigor and humility, and be prepared to accept whatever answer the universe provides, even if it rewrites the story of our planet's relationship with its star. The following sections are that act of leaning in. Let's begin with the source, the sun itself in a state of rage. To understand the force that may have reached out and touched the Earth with such improbable timing, we must first stare directly into the heart of the eruption. We must dissect the anatomy of a solar tantrum. The sun, for all its life-giving constancy, is a turbulent ball of plasma, a churning dynamo where magnetism is born from motion. solar cycle 25, the current approximately 11-year period of magnetic activity, was predicted by many models to be a quiet one, a feeble echo of the powerful cycles that preceded it. The Sun, it seems, did not read the forecasts. Instead of a gentle ramp-up, cycle 25 has been assertive, even defiant. Sunspot numbers have consistently overshot predictions, and the frequency of flares and coronal mass ejections has kept space weather forecasters in a state of perpetual vigilance. The stage was set not for a whisper, but for a scream. The actors in this drama were two conjoined sunspot regions, 4298 and the now infamous 4299. When they rotated into view on the Earth-facing solar disk, they carried the hallmarks of danger. To the trained eye-analyzing magnetogram data, these were not simple bipolar spots. They were complex, sprawling regions where magnetic field lines of opposite polarity were crammed together in a chaotic stress tangle. Imagine taking the magnetic field of 1,000 bar magnets, twisting them, knotting them, and then submerging them in a sea of superheated, electrically conducting gas. That is the reality of a magnetically complex active region. The photosphere, the Sun's visible surface, appears cooler in these spots because the intense magnetic pressure suppresses the convective uprising of hotter plasma from below, creating darker patches against the bright solar backdrop. But this darkness is deceptive. It is not an absence of energy. It is a concentration of stored, pent-up magnetic energy. The sequence that culminated in the 1347 event began with a warning shot. Hours before the main event, Region 4299 unleashed an M1.1 class flare. In the grand hierarchy of solar explosions, this was a moderate event, enough to cause brief radio blackouts on the sunlit side of Earth, enough to register on monitors, but not enough to trigger major alerts. Yet, in the nuanced physics of solar magnetism, this precursor flare was critically important. Think of it as a small tremor along a geological fault. It relieves a small amount of stress, but in doing so, it can destabilize the surrounding structure, transferring stress to neighboring areas and bringing the entire system closer to a catastrophic failure. The M1.1 flare was the Sun's equivalent of a tectonic creak. It reconfigured the local magnetic architecture, unwinding some field lines, but tightening others, priming the region for a far more violent release. Then came the detonation. At 1347 UT, the magnetic tension exceeded its breaking point. The process is known as magnetic reconnection. Picture those enormously twisted rubber bands of magnetic flux finally snapping. When they do, they don't just break. They violently reconfigure themselves into a lower energy, simpler arrangement. The colossal difference in energy between the twisted state and the relaxed state must go somewhere. It is converted with breathtaking efficiency into heat, light, and motion. In the reconnection zone, temperatures soar to tens of millions of degrees. Electrons and protons are whipped to nearly the speed of light. A flash of electromagnetic radiation erupts across the entire spectrum, from long wavelength radio waves to incredibly energetic X-rays and gamma rays. This is the solar flare, the brilliant impulsive flash captured by the X-ray sensors on the GOES satellites. The M8.1 classification places it at the very top of the medium category, brushing the threshold of an X-class event, the most powerful category we measure. The flare's brightness in X-rays is what lit up detectors across the inner solar system, an undeniable beacon of magnetic catastrophe. But the flare, for all its brilliance, was merely the flashbulb. The real kinetic threat was already being born in the Sun's outer atmosphere, the corona. This is where the coronagraphs on the SOHO and Stereo spacecraft tell the second, and arguably more important, chapter of the story. By blocking the dazzling photosphere, these instruments reveal the faint, structured glow of the million-degree corona. The footage from this event is not of a simple, expanding bubble. It shows a two-stage eruption, a feature that immediately caught the attention of solar physicists. First, a faint, fast-moving shock front ripples outward, a propagating wall of compressed plasma driven ahead of the main ejector. This shock is the bow wave of the explosion, ploughing through the ambient solar wind. Then, following closely behind, comes the dense core of the coronal mass ejection itself, a billion-ton cloud of magnetized plasma, a coherent structure carrying with it the twisted magnetic field, called a flux rope, that was once anchored to the sun's surface. The full halo appearance is the key diagnostic for Earth impact. When a CME is headed directly toward or away from us, it appears to expand as a symmetrical ring or halo around the occulting disk. There is no ambiguity in the imagery from that day. A perfect, glowing halo blossomed around the sun, meaning the bulk of the ejected mass was on a trajectory that intersected Earth's orbit. This was not a glancing blow or a near miss. It was a direct hit. The CME's speed was calculated at over 2,000 kilometers per second, exceptionally fast, placing it in the top percentile of such events. Speed matters because it determines the transit time to Earth and the violence of the eventual impact. A CME this fast would cover the 150 million kilometers to Earth in less than 24 hours. Let's pause to understand what this interplanetary projectile means when it arrives. Earth is not a naked rock in the solar wind. It is shielded by its magnetosphere, a teardrop-shaped bubble of magnetic influence generated by the dynamo in our planet's core. This magnetic shield deflects the constant stream of charged particles from the sun, channeling them around the planet and toward the poles where they create the auroras. A normal solar wind stretches the magnetosphere but doesn't fundamentally breach it. A coronal mass ejection, especially a fast, dense one like this, is a different beast entirely. The impact is a two-phase assault, perfectly mirrored by the CME's own double structure. First, the leading shock front slams into the magnetosphere. This sudden compression causes the entire magnetic field around Earth to jolt and ring like a bell, a phenomenon called a sudden impulse. Magnetic field lines are compressed on the day side and stretched into a long magneto-tail on the night side. Rapid fluctuations in the magnetic field are induced at the surface. Then, hours later, the main body of the CME arrives. Its potency depends on a critical factor, the orientation of its embedded magnetic field. If the CME's magnetic field is oriented northward, aligned with Earth's own north-pointing field, it largely slides around the magnetosphere. But if it is southward, anti-aligned, a catastrophic process called magnetic reconnection occurs on a planetary scale. Earth's field lines and the CME's field lines connect, effectively opening the magnetosphere and allowing the solar wind to pour directly into the polar regions. This injects enormous energy into the ionosphere and sets powerful electrical currents flowing in the upper atmosphere and, crucially, induces mirroring currents in the ground below. This is a geomagnetic storm, and its effects are well catalogued. Intense auroras visible at mid-latitudes, induced currents in power grids that can trip safety systems, or even cause transformers to fail, increased satellite drag, disruption of high-frequency radio communications, and degradation of GPS accuracy. All of this is standard space weather. The Space Weather Prediction Center in Boulder, Colorado, issued alerts for a strong G3 geomagnetic storm in the hours following the CME's impact. This event was officially recognized, tracked, and warned about by the governmental infrastructure designed for that purpose. It was a significant space weather event, but by the official definitions and models, its consequences were expected to be technological and atmospheric. Nowhere in the NOAA alert bulletins, nor in any operational space weather forecast model, is there a line item for increased seismic hazard. The physical chain of effects, as officially understood, stops at the upper atmosphere and the ground level power grid. The idea that the energy could penetrate deeper, influencing the mechanical stability of the crust, is absent from the paradigm. This is the boundary we are probing. We have an exceptionally well-characterized solar storm. Its genesis, its morphology, its interplanetary journey, and its magnetospheric impact are all documented. We also have a sharply timed, powerful earthquake. The official models see these as parallel lines that never meet. The data from that Tuesday suggests, with unnerving precision, that the lines may have crossed. To understand how, we must now turn from the fury of the sun to the fracture in the earth. Alaska is a land of sublime, brutal beauty, a place where the planet's raw tectonic forces are written plainly across the landscape in jagged mountains, deep fjords, and volatile volcanoes. It sits astride the boundary between two of Earth's great tectonic plates. The Pacific Plate, a vast slab of oceanic crust, is diving, subducting, northwest beneath the North American Plate at a rate of several centimeters per year. This is the Aleutian megathrust, part of the infamous Ring of Fire. The process is not smooth. The plates stick. Stress accumulates over decades, and eventually, that stress overcomes friction in a sudden catastrophic slip. This makes Alaska one of the most seismically active regions on the planet. Earthquakes are not anomalies here. They are a geological constant. Magnitude 6 events are routine. Magnitude 7 events, like the one that struck at 1347 UT, happen every few years. The historical record holds the scars of monsters. The 1964 Great Alaska Earthquake, a magnitude 9.2 megathrust event that remains the second most powerful ever recorded globally, reshaped the coastline and sent tsunamis across the Pacific. So, a magnitude 7.0 earthquake in Alaska is, by itself, not extraordinary. It is part of the background tectonic noise. What makes the event of that Tuesday exceptional is not its location or its size, but its exquisitely precise timing and the peculiar details of its sequence. The rupture occurred at a shallow depth, placing its hypocenter within the brittle upper crust. Shallow earthquakes are often more destructive because the seismic waves have less rock to travel through before reaching the surface, meaning less energy is absorbed along the way. The initial seismic waves painted a picture of a strike-slip mechanism, a fault where two blocks of crust slide past each other horizontally. This suggested the rupture was not on the main subduction megathrust itself, but on a secondary fault within the complex, fractured maze of the overriding North American Plate, a fault that was being stressed and twisted by the larger subduction process. The seismograms tell a story of violence. The first P-wave arrivals were sharp, followed by the stronger S-waves, and then the long, rolling surface waves that caused the most shaking and damage. Ground acceleration was significant, strong enough to be felt hundreds of kilometers away, to crack roads, trigger rockfalls in mountainous areas, and send a jolt of fear through communities. But it was the aftermath, the aftershock sequence, that provided the first seismic clue that this event was somewhat unusual. Within hours, over 150 aftershocks were detected, a remarkably energetic and prolific swarm. Several of these exceeded magnitude 5.0, events that would be headline news in less active regions. This level of productivity suggests the main shock did not simply release stress on a single fault plane. It efficiently transferred stress to a network of surrounding faults, essentially shaking loose a whole section of crust that was critically loaded. It was as if the main rupture popped one cork in a pressurized system, and the aftershocks were the fizz of gas escaping from a multitude of tiny cracks around it. Now we arrive at the central puzzle of timing. Statistically, with roughly 1 magnitude 7+ earthquake occurring somewhere on Earth each month, and with the Sun producing M-class flares several times a month during solar maximum, random coincidences are inevitable. If you define your correlation window broadly, say an earthquake occurring within 3 days of a major flare, you will find many such matches purely by chance. This is the statistical quagmire that has doomed many previous attempts to prove a solar seismic link. The correlation disappears into the noise of two frequent independent processes. But what happens when you shrink the window? What about an earthquake within an hour of a flare? Within a minute? The probability of a random coincidence plummets. The Alaska event presents us with a window of 1 second. This is not a statistical window. It is a temporal pinpoint. It moves the event from the realm of possible coincidence into the territory of profoundly suspicious. Mainstream seismology has a ready answer for this. It is a profound coincidence, nothing more. The energy scales are simply incompatible. The total seismic energy released in a magnitude 7.0 earthquake is on the order of 2 x 10⁻15 joules. The electromagnetic energy delivered to Earth's surface by even an extreme geomagnetic storm is many orders of magnitude smaller. From a pure energy budget perspective, the sun's influence seems laughably insufficient to cause a rupture. Furthermore, earthquakes are driven by mechanical stresses built up over centuries from plate motions. The final trigger is believed to be a highly local process. A tiny patch of fault reaches a critical stress threshold. A pore pressure changes due to fluid migration, or a small creep event transfers stress to a locked segment. The idea that a signal from 93 million miles away could provide the final nudge seems to most seismologists physically implausible. But the counter-argument, often voiced from the interdisciplinary fringes, is one of non-linear thresholds. Consider a boulder balanced on a cliff's edge. It holds immense gravitational potential energy. The cause of that energy is the Earth's gravity, acting over geologic time to position it there. The boulder's eventual fall will release that energy catastrophically. Yet the trigger for the fall is not a force comparable to gravity. It is the tiny, final nudge from a bird landing on it, a gust of wind, or a minute tremor. The nudge doesn't supply the energy. It releases energy already stored. Could a fault be that boulder? Could centuries of tectonic stress load a fault to a state of such critical instability that an infinitesimally small external perturbation, a passing tidal force from the moon, a change in atmospheric pressure from a storm, or an electromagnetic pulse from the sun, could provide the final catalytic push? This is the straw that breaks the camel's back hypothesis. It doesn't require the sun to supply earthquake energy. It only requires the sun to provide a timely straw. Some studies have tentatively suggested that such weak triggering might be possible. Research has shown statistically marginal but persistent correlations between earth tides, the gentle cyclical stretching of the crust from the gravitational pull of the moon and sun, and the timing of small earthquakes. The tidal force is astronomically weak compared to tectonic forces, yet it appears to have a modulating effect. If the weak, cyclical tug of the moon can matter, could the acute, powerful electromagnetic punch of a solar storm matter more, under the right conditions? The conditions would have to be exquisitely specific. A fault already at a critical point of failure, a specific orientation and conductivity of the rock to efficiently channel induced currents, and a solar storm of particular intensity and magnetic configuration. The Alaska earthquake, by itself, proves none of this. It is a single, stunning data point. To move from an intriguing anomaly to a testable hypothesis, we need more than just two events sharing a timestamp. We need a plausible physical bridge between them. This is where the investigation takes its most controversial turn. If the sun's flare provided the spark and the Earth's fault provided the tinder, we must look for evidence of the flame, the conduit that carried the signal from the magnetosphere to the hypocenter. We must search for an electromagnetic fingerprint etched into the planet's background hum at the exact moment both the sun erupted and the ground broke. This leads us into the elusive, noisy, and contentious world of Schumann resonances and global electromagnetic anomalies. The Earth is not just a rock, it is an electrical instrument. It exists within a self-generated magnetic field, bathed in the conducting plasma of the ionosphere above and possessing conductive layers like salty groundwater and ocean below. Between the conductive ionosphere and the conductive ground lies a resonant cavity, a spherical shell of insulating atmosphere that can trap and amplify certain frequencies of electromagnetic waves. This cavity has a natural resonance, much like a bell has a characteristic ring when struck. The primary source of strikes is global lightning activity. Every bolt pumps electromagnetic energy into this cavity. The resulting standing waves are known as Schumann resonances, named after the physicist Winfried Schumann, who predicted them in 1952. The fundamental frequency is about 7.83 Hz, with harmonics at approximately 14.3, 20.8, 27.3 Hz, and so on. You can think of it as the planet's permanent ultra-low frequency hum, its electromagnetic heartbeat. A global network of sensitive magnetometers and antennas, operated by both research institutions and dedicated amateurs, monitors these resonances. Under normal conditions, the amplitude of the Schumann peaks varies predictably with the daily cycle of global thunderstorm activity, which migrates with the sun's illumination. But during powerful geomagnetic storms, this orderly picture can change. The influx of energetic particles and the violent compression and distortion of the magnetosphere can energize the ionosphere, changing its conductivity and geometry. This can inject additional energy into the cavity, causing the Schumann resonances to spike in amplitude, broaden, or show unusual spectral features. These disturbances are a documented fingerprint of severe space weather. Now, enter the claims from the fringes of this event. Shortly after the Alaska earthquake, reports began circulating online, primarily from alternative space weather and seismic forecast channels, about extraordinary electromagnetic anomalies detected at the critical time. Spectrograms, visualizations of frequency versus time, from monitoring stations, most notably one in Tomsk, Russia, were shared widely. They purported to show a massive broadband spike in electromagnetic energy across the Schumann resonance band, from near 0 Hz up past 25 Hz, peaking precisely at 1347 UT. The images were dramatic, a vertical red or yellow streak on the spectrogram, suggesting a sudden, global-scale electromagnetic scream coinciding with the solar flare and the earthquake. If genuine and global, such a signal could be the smoking gun, the tangible evidence of a planet-wide electrical disturbance connecting the two events. This is where extreme caution is mandatory. The field of natural electromagnetic phenomena is a notorious minefield of false positives and artifacts. The signals at these extremely low frequencies are incredibly faint, and the instruments required to detect them are highly susceptible to interference. A spike on a single spectrogram without rigorous context is scientifically worthless. What was the local weather? A nearby thunderstorm can produce a huge spike. Was there human-made interference? Power line fluctuations, industrial machinery, or even a passing vehicle can generate signals. Was the instrument properly calibrated and its time synchronized? A software glitch or a loose connection can create spectacular artifacts. The internet is littered with anomalous Schumann resonance charts that later prove to be nothing more than local lightning or instrument failure. For a detection to be credible, it must be global and coherent. Multiple, geographically separated monitoring stations in Russia, Europe, North America, the Southern Hemisphere would all need to show the same anomalous signature at the same universal time. Local weather data from each site would need to confirm an absence of thunderstorms. The signal would ideally need to precede the seismic rupture by at least several seconds to suggest a triggering cause, rather than follow it, as earthquakes themselves can generate electromagnetic signals through processes like the piezoelectrification of stressed rocks. This level of rigorous cross-verification is almost never presented alongside the initial sensational claims. The scientific discipline that studies these potential connections is known as seismoelectromagnetics. For decades, researchers have hunted for reliable electromagnetic precursors to earthquakes, hoping to find a signal that could serve as an early warning. The physics in the lab is clear. Certain rocks, like quartz-rich granite, generate small electrical potentials when mechanically stressed. The piezoelectric effect. In principle, a fault under immense tectonic stress could generate detectable electromagnetic emissions before it fails. In practice, despite numerous claims and dedicated research programs, no such precursor signal has ever been consistently verified and accepted by the broader scientific community. The signals are either too weak, too inconsistent, or too easily confused with ubiquitous background noise. So, we are left with a tripartite mystery of highly unequal credibility. Component 1. The solar storm. Rock solid, documented by the world's premier space agencies. Component 2. The earthquake. Equally solid, documented by global seismic networks. Component 3. The electromagnetic bridge. This is the weak link, a collection of unverified, poorly contextualized claims from fringe sources. The combination is intellectually tantalizing but evidentially frail. It allows for two starkly different interpretations. Interpretation 1, the mainstream view. We have two definite, unrelated events and a set of unconfirmed, likely spurious signals from the noisy fringe. The temporal coincidence, while striking, is just that, a 1 in a million roll of the cosmic dice that is bound to happen eventually. Interpretation 2, the speculative investigation. The temporal coincidence is too precise to ignore. The reported electromagnetic anomalies, while messy, point toward a real global disturbance that may be the hidden mechanism linking the first two events. The burden of proof, however, rests overwhelmingly on the proponents of the second interpretation. To assess which interpretation is more likely, we must step back from this single event and ask the broader questions. What does the collective weight of statistical evidence over decades say? What physical mechanisms could possibly allow such a connection? And what would it take to move this question from the realm of internet mystery to legitimate mainstream science? We begin by taking inventory of what we truly know and what remains pure speculation. Let us pause here at the midpoint of the investigation and take forensic stock. What can we assert with high confidence? What remains ambiguous? And where does the border between evidence and speculation lie? Clarity on these points is essential before we delve into deeper mechanisms and broader contexts. With confidence, we can state 3 facts. A significant solar eruption occurred, an M8.1 flare and a fast, Earth-directed full halo coronal mass ejection originated from Sunspot region 4299 at 1347 UT. This was recorded by multiple satellite observatories, SDO, SOHO, GOES, and triggered official geomagnetic storm warnings from NOAA's Space Weather Prediction Center. The event's reality, timing, and characteristics are not in dispute. A significant seismic rupture occurred. A shallow magnitude 7.0 strike-slip earthquake struck southern Alaska at 1347 UT. It was recorded by the Global Seismic Network, produced a vigorous aftershock sequence, and caused documented ground shaking. Its reality, timing, and location are not in dispute. The temporal coincidence is extraordinary. The synchronization of these two powerful events from different domains, down to the same second, is exceptionally rare. It represents the narrowest possible correlation window and cannot be easily dismissed as a statistical inevitability given the precise timestamp alignment. With significantly less confidence, we can note a 4th element. 4. Unverified electromagnetic anomalies were reported. Claims of anomalous spikes in Schumann resonance data and other magnetometer readings at the time of the events exist. However, these reports lack the rigorous metadata, global coherency, and independent verification required to treat them as reliable scientific data. They remain intriguing but unconfirmed anecdotes. Now, what can we not claim? We cannot claim a proven causal mechanism linking solar flares to earthquakes. The physics required for such a direct, energetic link is not established in peer-reviewed literature and faces formidable theoretical hurdles, primarily the colossal energy mismatch. We cannot claim this single event proves a universal relationship. One coincidence, no matter how striking, does not establish a pattern. The scientific method requires repeatability and predictive power. We cannot claim that mainstream science is ignoring conclusive proof. The prevailing consensus in both heliophysics and seismology is one of deep skepticism, based on decades of research that has largely failed to find robust, reproducible correlations. This skepticism is not a conspiracy of silence. It is a default position demanded by the absence of compelling evidence. So, where does this leave us? With an anomaly. In science, anomalies are not conclusions. They are starting points. They are the irregularities in the data that prompt us to check our instruments, question our assumptions, and, if the anomaly persists, to potentially expand our theories. The Alaska synchronization is a first-class anomaly. It is too clean, too precise to be immediately discarded. It demands a follow-up question. If this were a causal connection, how could it possibly work? This shifts our investigation from data forensics to theoretical plausibility. The energy budget objection is the tallest hurdle. A magnitude 7 earthquake releases something like 2 petajoules, 2x 10 war 15J of energy. The total electromagnetic energy input from even a severe geomagnetic storm into the Earth system is orders of magnitude smaller, perhaps in the terajoule range, 10-12J or less. Directly powering the quake with the storm is impossible. This is why the triggering or threshold hypothesis is the only viable conceptual path. The solar storm would not be the engine, it would be the spark. The tectonic stress accumulated over centuries provides the fuel. In this model, the electromagnetic disturbance from the sun needs only to perturb the fault system in a way that changes the local stress field by a tiny amount, altering fluid pressures in fault zone pores, causing minute thermal expansion, or via piezoelectric effects, adding a tiny mechanical stress to critically loaded crystals. If the fault is truly on the brink, such a minuscule nudge could advance the timing of a rupture that was inevitable by hours, days, or perhaps milliseconds. This moves the question from, is there enough energy, to, could this specific form of energy be efficiently delivered to the right place, in the right way, to matter? It becomes a problem of coupling efficiency, rock physics, and fault zone vulnerability. It is a vastly more nuanced and difficult question to answer. It is also a question that resides in the no man's land between scientific disciplines, which explains why it has not been conclusively answered. Solar physicists model the solar-wind magnetosphere-ionosphere coupling. Geoelectromagnetists model how telluric currents flow in the Earth's crust. Seismologists model stress and fracture on faults. Few researchers have the funding, mandate, or expertise to model the entire attenuated chain from solar corona to hypercenter. Therefore, the current verdict is one of informed curiosity, not acceptance. We have an anomaly worthy of serious, interdisciplinary investigation. We do not have evidence demanding a paradigm shift. The path forward is not to declare a solar seismic link proven, but to define what would constitute proof and to systematically build the tools and data sets needed to seek it. This leads us to the next phase of our exploration, a detailed examination of the proposed physical bridges that could, under perfect and perhaps rare conditions, turn our star into a geological trigger. If we are to entertain the possibility that the sun's outburst reached into the crust to nudge a fault, we must construct a hypothetical pathway. We must follow the energy, step by attenuated step, from the corona of the sun to the hypocenter in Alaska. The journey is one of transformation, from kinetic and magnetic energy in plasma to electromagnetic energy in space, to induced electrical currents in the Earth's environment, and finally to a minute mechanical stress in a specific volume of rock. Each step involves well-understood physics, but the efficiency of the coupling diminishes dramatically at each transition. The question is whether, under a perfect storm of conditions, enough signal could survive the journey to make a difference. Step 1. From Sun to magnetosphere. This step is the most robust. The coronal mass ejection, carrying its embedded southward magnetic field, compresses Earth's magnetosphere. The sudden change in the planetary magnetic field, measured by the sudden impulse index, induces powerful electric fields in near-Earth space, according to Faraday's law of induction. A changing magnetic field creates an electric field. These electric fields, which can reach thousands of volts, drive massive electrical currents in the ionosphere, the auroral electrojets that circle the polar regions. This is standard, observed geospace physics. Step 2. From magnetosphere, ionosphere to the ground. The ionospheric currents, in turn, create secondary mirror image currents that flow in the Earth itself. These are known as telluric currents. They are the reason geomagnetic storms threaten power grids. The fluctuating magnetic field induces voltages in long conductors like transmission lines and pipelines. These telluric currents flow through the crust, seeking paths of least electrical resistance. Their strength and distribution depend on the intensity of the geomagnetic disturbance and the subsurface electrical conductivity structure, which varies greatly depending on rock type, fluid content, and temperature. Step 3. From telluric currents to fault zone stress. This is the critical, speculative leap. How could these diffuse, near-surface electrical currents influence a fault zone at depth? Several hypothetical mechanisms have been proposed. The piezoelectric effect. Quartz, a ubiquitous mineral in continental crust, is piezoelectric. Apply mechanical stress, and it generates an electric charge. The effect also works in reverse. Apply an electric field, and the crystal deforms minutely. If a telluric current pulse passes through a volume of quartz-rich rock surrounding a critically stressed fault, could the induced electric field cause tiny mechanical distortions that add to the local shear stress, pushing it over the failure threshold? Electrokinetic, streaming potential. Fault zones are often saturated with fluids. When an electric field is applied across a porous, fluid-filled medium, it can induce fluid flow, electroosmosis. Conversely, forcing fluid through a porous medium generates an electric field, the streaming potential. A telluric current could, in theory, perturb fluid pressures within the fault zone's intricate pore network. Since fluid pressure is a primary controller of fault friction, higher pressure reduces friction, making slip easier. A small, rapid pressure change could trigger a rupture. Joule. Heating. As telluric currents flow through resistive rock, they generate heat. This heating is generally minuscule and diffuse. However, if currents were somehow concentrated within a fault zone, perhaps due to its altered, more conductive mineralogy, localized resistive heating could theoretically expand fluids or minerals, altering local stresses. Electromagnetic force, Lorentz force. The telluric current is a flow of charged particles. Earth has a steady background magnetic field. A charged particle moving in a magnetic field experiences a force perpendicular to its motion, the Lorentz force, Could the combined effect of billions of such tiny forces on ions within a fault zone translate into a net mechanical stress? Each of these mechanisms is physically plausible in a laboratory setting. Scaling them up to crustal dimensions and energy levels is where the problems arise. The effects are incredibly weak. The telluric currents themselves are diffuse, spread over vast areas. Fault zones are complex, heterogeneous environments. For any of these mechanisms to work as a trigger, they would require an almost miraculous focusing of energy. A fault already at the absolute pinnacle of stress, a subsurface conductivity structure that channels currents directly into the fault core, and a solar storm of specific intensity and waveform to deliver the optimal pulse. This is why the hypothesis remains fringe. The chain of ifs is long. If the fault is critically stressed, if the rock has the right mineralogy, if the subsurface conductivity focuses currents there, if the solar storm has the right magnetic orientation and time profile, then maybe a triggering effect is possible. To mainstream seismology, this reads as a series of implausible contingencies that, even if true, would produce an effect so rare and unpredictable as to be irrelevant for hazard forecasting. To the open-minded investigator, it represents a frontier of complex systems where non-linear responses can occur. Recent, more mainstream research has explored subtler, less direct connections. A 2023 study examined whether large-scale solar heating patterns transmitted through atmospheric tides and the resulting loading on the crust could statistically influence global seismicity at a barely detectable level. Another line of inquiry looks at the possible role of cosmic rays, whose flux is modulated by the solar wind. The hypothesis suggests cosmic rays could influence atmospheric ionization and thus thunderstorm activity, which in turn could affect the crust through electromagnetic or pressure changes. These ideas are less dramatic than direct electromagnetic triggering, but operate on similar principles of indirect weak coupling across system boundaries. The takeaway from this dive into mechanisms is that a direct, powerful solar trigger for earthquakes is physically implausible. However, a weak, conditional, threshold-based influence, where the sun acts as the final straw for a fault already loaded to breaking, cannot be ruled out by first principles. It occupies a grey zone of possibility. Proving it or disproving it requires moving beyond single-event anecdotes and mechanism speculation. It requires a cold, hard look at the numbers. Does the historical data, when analysed without bias, show any statistical hint that earthquakes and solar activity are connected, even weakly? This leads us to the contentious world of correlation studies, where pattern-seeking minds and noisy data have battled for decades. If solar activity influences seismicity, even as a subtle modulator, the signal should be etched into the historical record. We have over a century of reliable sunspot data, decades of detailed geomagnetic indices, and extensive global earthquake catalogues. Statistics should be the arbiter. The literature, however, is a battleground of contradictory conclusions, methodological disputes, and accusations of cherry-picking. To understand why there is no consensus, we must delve into the inherent pitfalls of this kind of research. The fundamental challenge is the high base rate of both phenomena. The sun is almost always active to some degree, especially during the 11-year solar maximum. Earthquakes above magnitude 5.0 occur somewhere on the planet almost daily. Magnitude 7.0 events happen monthly on average. With two frequent independently occurring processes, random coincidences are guaranteed. If you search long enough through decades of data, you will inevitably find periods where solar storms and large earthquakes appear clustered. The human brain is wired to notice and remember these clusters, while ignoring the vast stretches of time where storms and quakes are out of sync. This is confirmation bias. Researchers combat this by applying rigorous statistical tests to the entire dataset. They might ask, during the 24 hours following all X-class solar flares in the last 50 years, Were large earthquakes more frequent than during randomly selected 24-hour periods? Or they might correlate annual sunspot numbers with annual global seismic energy release. Dozens of such studies have been conducted. The majority find no statistically significant correlation. The earthquakes appear randomly distributed with respect to solar activity. A comprehensive 2013 analysis that examined hundreds of major flares and thousands of significant earthquakes concluded that any apparent link vanished under proper statistical scrutiny. However, a minority of studies claim to find signals. A 2020 paper suggested a slight increase in the probability of magnitude 5.5 plus earthquakes globally in the 24 hours following a severe geomagnetic storm. The effect was tiny, increasing the odds from a baseline level by a minuscule fraction of a percent. Another line of research looks for periodicities. Since the sun rotates every 27 days, recurrent solar wind streams from coronal holes can create 9, 13.5, or 27-day patterns in geomagnetic activity. Some analyses of earthquake catalogues claim to find faint, statistically weak periodicities at these same frequencies, hinting at a solar-driven rhythm in seismic release rates. Why the discrepancy? Methodological choices dramatically influence outcomes. Selection of time window. Is the effect immediate, within minutes, delayed by hours, or lagged by days? Without a strong physical model to dictate the lag, researchers can, consciously or not, test multiple windows until they find one that shows a correlation, a practice known as p-hacking. Selection of event thresholds. What defines a solar event? M5 flares, X-class only, geomagnetic storms with a KP index above 7. Similarly, what magnitude of earthquake counts? Different thresholds yield different results. Spatial filtering. Should we look at global seismicity or only in specific tectonic regions, e.g. subduction zones, mid-ocean ridges? If the effect is contingent on local geology, like conductive crust, a global analysis might dilute a real but localized signal. Handling of aftershocks. Aftershocks are not independent events. They are caused by the main shock. Including them in the count can artificially inflate apparent clustering after a solar event if a large independent quake happens to coincide. Perhaps the most damning criticism is the multiple comparisons problem. If you test enough different hypotheses, solar flares versus quakes in Japan, versus quakes in California, versus global quakes using 10 different time windows and 5 different magnitude thresholds, you are virtually guaranteed to find some combination that shows a statistically significant result purely by chance. Proper scientific practice requires pre-registering a specific hypothesis and test before looking at the data, a standard rarely met in this field. The statistical reality, therefore, is murky. The bulk of careful, large-scale studies suggest no meaningful link. The few positive signals are weak, marginally significant, and difficult to replicate. This is precisely what the scientific community would expect if the true effect were either non-existent or so vanishingly small and conditional that it is swamped by noise in all but the most exceptional, cherry-picked circumstances. The Alaska event represents the ultimate cherry pick, a single stunning coincidence pulled from decades of data where such precise timing did not occur. So, does statistics settle the debate? For mainstream science, the answer is yes. The absence of a robust, reproducible statistical signal across the full dataset is sufficient to dismiss the hypothesis as unproven and probably unimportant. For the curious investigator, the Alaska event and a handful of other historical odd couples suggests the statistics might be missing something. Perhaps the effect is not a broad average increase in seismicity, but a rare high-impact trigger that only occurs when a specific severe solar storm meets a specific critically poised fault. Such black swan events would not show up in broad correlational studies. They would be lost as statistical outliers. Detecting them would require a different approach, a forensic, case-by-case analysis of the most suspicious coincidences, armed with detailed data on both the solar storm and the local geological geoelectrical conditions. This brings us back from broad statistics to specific anomalies. What other peculiar features, beyond timing, make the Alaska event worthy of this deeper forensic look? Beyond the stark temporal coincidence, the event of that Tuesday is wrapped in a series of secondary peculiarities. These are the narrative hooks, the details that transform a dry data point into a compelling mystery. They range from the physically notable to the wildly speculative. Examining them requires separating observational fact from interpretive storytelling, a crucial skill in navigating this frontier. Anomaly 1. The double explosion CME morphology. As noted in the solar analysis, the coronagraph imagery showed a distinct two-part structure, a leading shock front followed by the dense plasma cloud. This is not unheard of, but it is a feature of particularly complex and energetic eruptions. Some researchers hypothesize that such a structure could create a more potent and complex impact on the magnetosphere. The initial shock provides a sharp, impulsive compression, setting the entire system ringing at high frequencies. The following main cloud, with its strong southward magnetic field, then drives sustained, deep reconnection. This 1-2 punch could, in theory, induce a broader spectrum of telluric currents, both fast, transient pulses from the shock and stronger, steadier currents from the main phase, potentially increasing the chance of interacting with a resonant fault system. While intriguing, it's important to note that many major geomagnetic storms have been caused by simpler CMEs. This feature makes the storm interesting, but not uniquely supernatural. Anomaly 2. Precursor seismic quiet. In the 2 weeks leading up to the magnitude 7.0 event, the same region of Alaska experienced a magnitude 6.0 earthquake. Typically, a shock of that size is followed by a decaying sequence of aftershocks as the crust adjusts. According to some analyses, the aftershock sequence following that M6.0 event was anomalously quiet. Fewer aftershocks than empirical laws would predict. One interpretation is that the M6.0 event did not fully release the regional stress. Instead, it transferred stress to a neighboring, locked fault segment, leaving the area in a state of heightened, silent tension. This created a stress shadow, or a seismic gap, that was primed for a larger release. In this narrative, the region was a tectonic powder keg, and the solar storm provided the spark. However, seismicity is inherently variable. Quiet periods are common and not reliably predictive of large events. This anomaly is suggestive, not diagnostic. Anomaly 3. Claims of pre-seismic electromagnetic signals. Separate from the global Schumann resonance claims, there were unverified reports from amateur investigators of unusual very low frequency, VLF, radio wave propagation anomalies in the hours before the Alaska quake. The idea is that stress-induced rock fracturing in the build-up to a major rupture could generate ultra-low-level electromagnetic emissions that subtly affect the lower ionosphere, changing how VLF signals bounce between the ground and the ionosphere. This is the holy grail of seismoelectromagnetics, a reproducible precursor. Yet, as with all such claims, these reports lack rigorous validation, control for other ionospheric drivers, like the solar storm itself, and independent replication. They remain in the realm of intriguing anecdote. Anomaly 4. The geometry claims. Fringe territory. This is where the investigation brushes against pure pseudoscience. Some commentators, often in alternative media circles, have pointed out that the epicenter of the Alaska earthquake lies on a great circle line connecting ancient sites like the Giza pyramids, Nazca lines, and Angkor Wat. The implication is that these sites were built on planetary energy grid nodes or ley lines that are also seismically and electromagnetically sensitive, and that the solar storm activated this grid. Let's be unequivocal. There is no scientific evidence for a planetary energy grid influencing seismicity. The Earth's tectonic plates, fault lines, and seismic zones are explained entirely by plate tectonic theory. With thousands of ancient sites across the globe, drawing lines between a select few will inevitably intersect modern earthquake locations purely by chance. A classic example of apophenia, seeing meaningful patterns in random data. While this narrative is compelling to the human love for hidden order and ancient wisdom, it is a distraction from the physical science. It is important to acknowledge its existence in the public discourse around such events, if only to clearly demarcate the boundary between speculative physics and mystical pattern seeking. Why do these anomalies matter? Collectively, they build a narrative of significance. The double CME suggests a uniquely powerful solar event. The seismic quiet suggests a fault at a critical state. The unverified EM signals hint at a pre-rupture disturbance. Even the geometric coincidence, though almost certainly meaningless, adds an archetypal layer of mystery. Together, they create a story that feels too rich to be mere coincidence. But science must be wary of narrative fallacies. A compelling story is not evidence. Each anomaly must be evaluated on its own, hard merits. The double CME is a real feature, but its geo-effectiveness, while potentially enhanced, is not revolutionary. The seismic quiet is real, but not uncommon or predictive. The EM signals are unconfirmed. The geometry is coincidental. The responsible approach is to treat these anomalies as flags, not proofs. They are the details that make this case a priority for further study. They suggest that if we are going to invest resources in testing the solar triggering hypothesis, this event, with its clean timing, interesting solar morphology, and suggestive seismic context, is the ideal candidate for a forensic deep dive. But to perform that dive, we need a specific plan. We need to know what data would constitute a smoking gun and how we should collect it going forward. We must move from analyzing this past event to designing the future investigation. If we are serious about resolving the question of solar-triggered seismicity, we must define the standards of evidence. A single coincidence, no matter how dramatic, will never be enough. We need a reproducible, multi-pronged detection that can survive intense scrutiny. Drawing inspiration from how other fringe ideas, like gravitational waves, became mainstream science, we can construct a forensic checklist, a set of criteria that any future claimed event must meet to be taken seriously. 1. Precise, multi-instrument time synchronization. The timing correlation must be exact and verified by instruments synchronized to universal time via GPS or atomic clocks. This means not just the flare and quake timestamp, but the precise onset of any alleged electromagnetic anomaly. Data must be timestamped to microsecond accuracy to rule out processing delays or clock drift. This requires a global network of instruments with disciplined timing. 2. Global coherence of the electromagnetic signal. The smoking gun is a geomagnetic or telluric signal that is global in nature but coherent in time. A true solar-induced signal should appear on magnetometers and Schumann resonance monitors worldwide at the same UT moment. Crucially, stations on the night side of the Earth, shielded from direct solar radiation and most thunderstorms, should also see it, ruling out local atmospheric effects. The signal's waveform should be consistent across widely separated sites, indicating a source in the global ionosphere or magnetosphere, not the local crust. 3. Exclusion of local and atmospheric noise. For each monitoring station recording the anomaly, simultaneous local environmental data must rule out false positives. This includes lightning detection network data to rule out thunderstorms, weather station data, wind, precipitation, and monitoring for human-made electromagnetic interference, power grid fluctuations, industrial activity. A signal that appears only at a single station during a local thunderstorm is worthless. 4. Correct temporal ordering. The sequence must be physically plausible for a triggering mechanism. The ideal evidence would show A. The solar flare X-ray pulse. Traveling at light speed, arrival is instantaneous. B. The onset of the global electromagnetic disturbance within seconds to minutes as the geomagnetic shock compresses the magnetosphere. C. The electromagnetic anomaly preceding the first seismic P waves by a measurable interval, even milliseconds, suggesting the EM pulse reached the fault before it ruptured. If the EM signal follows the seismic waves, it is likely generated by the earthquake itself and proves nothing about triggering. 5. Plausible local geoelectrical coupling. Once a temporally correlated global event is established, investigators must demonstrate a plausible pathway for energy to reach the specific fault. This requires detailed knowledge of the local subsurface. 3D electrical conductivity models from magnetotelluric surveys, the mineralogy of the fault zone, especially quartz content, the in situ tectonic stress field, and pore fluid pressures. The case is strengthened if the fault is known to be late in its seismic cycle, from GPS strain measurements, and if the subsurface conductivity structure would act as a waveguide, focusing telluric currents toward the hypocenter. 6. Statistical significance via prediction. The ultimate test is predictive power. If a specific mechanism is proposed, e.g., southward IMF CMEs with a shock front trigger quakes on critically stressed, quartz-rich faults with high subsurface conductivity, that hypothesis must make testable predictions. It should forecast where and when such triggering is most likely. Researchers would then monitor those specific locations during future extreme solar storms. Success would be defined as a statistically significant increase in observed triggering at the predicted locations and times compared to control periods, locations. 7. Peer-reviewed reproduction. The entire data chain, from raw satellite and ground-based data to the final analysis, must be published in a reputable peer-reviewed journal. The data and code must be made openly available so that independent teams can attempt to replicate the findings. The hypothesis is only validated when multiple skeptical groups using different analytical methods arrive at the same conclusion. Today, we have none of this. We have fragments. We have a temporal coincidence. Criterion 1, partially. We have unverified, non-global EM claims. Criterion 2, failed. We lack the integrated data infrastructure to properly test the others. Building that infrastructure is the necessary next step. It means installing synchronized broadband magnetometer and seismometer arrays in key tectonic regions. It means funding interdisciplinary projects that marry space weather models with crustal geoelectric and stress models. It means treating seismoelectromagnetics not as a fringe hobby, but as a serious, if high-risk branch of geophysics. The payoff for such an investment extends far beyond answering this single question. The sensor networks would revolutionize our understanding of space weather impacts on the ground, improve our mapping of Earth's interior electrical structure, and enhance both earthquake science and space weather forecasting. Even if the solar triggering hypothesis is ultimately disproven, the pursuit will have made our planetary monitoring infinitely more robust. This is how science turns speculation into knowledge, not by dismissal, but by designing a better test. As we contemplate building these tools on Earth, we must also lift our gaze. Our planetary system is not unique. The universe is a laboratory full of extreme examples of star-planet interaction. By studying these distant systems, we gain perspective on the potential, and the limits of the relationship between a star and its planets. This cosmic context is our final and perhaps most illuminating stop. To fully grasp the implications of a potential star-planet link here at home, we must see our solar system as one example among trillions. Recent discoveries in astronomy reveal a universe that is profoundly interconnected, where energy and influence flow across vast distances in ways that challenge simple, isolated models. Our investigation into a solar trigger for earthquakes is, at its heart, a question about connectivity. Does the sun's influence stop at the aurora, or does it thread deeper? Looking outward provides both sobering and enlightening parallels. Case Study 1, the dying planet, WASP 107b. About 650 light-years away, the James Webb Space Telescope has observed a planetary tragedy in action. WASP 107b is a hot Jupiter orbiting so close to its star that its atmosphere is being violently stripped away. Webb detected a massive comet-like tail of helium gas stretching far into space, direct evidence of the planet's atmosphere boiling off under intense stellar radiation and particle bombardment. Here, star-planet coupling is not subtle, it is catastrophic and direct. The star's energy is physically unbinding the planet, reshaping it over million-year timescales. This proves unequivocally that stars can have dramatic, physical effects on their planets beyond mere illumination. The mechanism is different, primarily extreme UV heating, but the principle is the same. Stellar output dictates planetary evolution and fate. Case Study 2, the synchronized filament, cosmic coherence. On a scale almost incomprehensibly larger, radio telescope arrays have discovered something astonishing. Vast filaments of galaxies, spanning hundreds of millions of light-years, rotating coherently as single structures. These galaxies, separated by voids of empty space so vast that light takes eons to cross them, are not moving randomly, they are choreographed. This suggests an underlying coherence in the cosmic web, likely governed by the gravitational influence of dark matter. It is a stunning example of synchronization emerging on a scale where we would expect only chaos. While the physics is entirely different from our solar terrestrial question, it reinforces a cosmic lesson. The universe is capable of creating precise large-scale connections that defy simple, localized explanations. Case Study 3, the lesson of gravitational waves. Just a decade ago, gravitational waves were a theoretical prediction on the fringe of detection. Skeptics argued the signals would be too weak, the instruments too flawed. Then LIGO heard the chirp of two black holes merging. Within years, a new field of astronomy was born. The transformation happened because of sustained investment in exquisitely sensitive, globally coordinated instrumentation and a community prepared to analyze the data. Gravitational wave science is the blueprint for how to investigate a faint, elusive signal, build a better detector, create a global network, share data openly, and let the evidence accumulate. The question of solar seismic coupling is today where gravitational waves were in the 1990s. A plausible idea, mired in noisy data and skepticism. Its resolution will follow the same path, or it will not happen at all. These cosmic perspectives frame our earthly mystery. They tell us that star-planet interactions can be transformative, WASP 107b. They tell us that synchronization across vast distances is a natural feature of the cosmos, galaxy filaments. And they tell us that patient, instrumental precision can unveil hidden layers of reality, gravitational waves. They argue against intellectual isolationism. They suggest it is parochial to assume we fully understand all the ways our star can affect our planet, the synthesis and the path forward. We end where we began, but with eyes wide open. On a Tuesday at 13:47 UT, the sun erupted and the earth shook in perfect, terrible unison. The official story calls it a coincidence. The available statistics offer no rebuttal. The physical mechanisms seem implausibly weak, The burden of proof remains squarely on those who see a connection. Yet, the coincidence is so precise, it irritates the mind. It refuses to be forgotten. It becomes an anchor point for a larger, more humbling realization. Our models of natural systems are incomplete. We have built our hazard assessments on the assumption of separated domains. Space weather here, earthquakes there. This may be a necessary simplification, but it may also be a critical vulnerability. The way forward is not fear, but focused curiosity. It is a call for instrumentation, deploying the forensic monitoring networks outlined in Part 9, interdisciplinary collaboration, breaking down the walls between heliophysics, geoelectromagnetism, and seismology, data transparency, making all relevant space and ground-based data openly accessible for independent analysis, patient investigation, accepting that this question may take decades and many extreme solar cycles to answer definitively. The stakes are practical. If there is even a 1% chance that a class of extreme solar storms can advance the timing of major earthquakes on critically stressed faults, that must be factored into our risk models for critical infrastructure, from power grids to nuclear facilities. It would represent a black swan hazard scenario for which we are currently blind. But beyond the practical, there is a philosophical stake. We live on a dynamic planet orbiting a dynamic star, embedded in a connected cosmos. To assume we have mapped all the important connections is a failure of imagination. Science progresses not by clinging to comfortable models, but by investigating the anomalies that poke holes in them. The Alaska synchronization is such an anomaly. It may be nothing, or it may be a whisper from a hidden layer of solar-terrestrial dialogue, a hint that the relationship between our star and our planet is deeper, more subtle, and more influential than we have dared to suppose. The sun will continue to storm. The earth will continue to quake. Our task is to watch both, with ever sharper eyes and ever more connected minds, and to have the courage to let the data tell us the true story of their relationship. The investigation continues.